Welcome once again to the world of electricity markets. I'm Keegan Trujillo Green, and this presentation is a companion series to my articles on how electricity markets work. In the last video, we learned the basics of electricity supply and demand, and in this one, we'll learn about locational marginal pricing and the effects of transmission. Let's get started. In the last video, we established that for a given market, at a given time, there is one market price. However, the electrical grid is complex, more complex than this, as you can see in the map. For the purposes of market modeling, the grid consists of multiple pricing nodes, each of which has its own market price and in that sense acts like a market. Such a setup is called nodal pricing or locational marginal pricing, abbreviated LMP. Sometimes the pricing nodes are organized into larger zones for simplicity, and one price is set throughout each zone. Such a setup is called, as you can imagine, zonal pricing. Following the cafe analogy from the previous video, each pricing node is analogous to one neighborhood of cafes. But of course, the grid is an electrical network, and power can be transferred between its nodes through long-distance transmission and distribution lines. This is as if the neighborhoods of cafes were interconnected by an intricate network of pipes. Like electricity, espresso wouldn't even have to be made in the neighborhood in which it's consumed, and supply does not need to equal demand within a grid node. Because quantities of power can be traded between grid nodes, the entire grid must be cleared as one market in order to maximize the system-wide welfare. The total welfare is generally higher with trade than without, and that's why trade takes place. However, the network is leaky. Transmission and distribution lines are not ideal wires and have electrical resistance depending on their type and length. Thus, some power is lost to heat for each unit of power transferred. These transmission losses are analogous to a cost of trade between grid nodes. Power transfer between nodes is still usually necessary and beneficial. For example, it is likely to be cheaper to use nuclear power transmitted over a great distance, with some lost along the way, than to use power from a nearby gas-fired plant. We need a way to model and account for the costs of trade when clearing the market, as they'll affect the optimal quantities of power and cause prices to differ between nodes. In general, each node affects all others. For the sake of simplicity, when demonstrating the effect of transmission losses on the electricity market, we'll assume a given transmission line to have a fixed efficiency, eta, defined as power out divided by power in. In the real world, even more complex transmission line models, which build upon the economic dispatch problem, are used when clearing the electricity market. Losing some power to heat is not just disadvantageous because it's wasteful. As transmission lines heat up, they expand, elongate, and start to sag. If a transmission line were to sag too close to a nearby object, like a tree, electricity will arc to the object and cause a short circuit, requiring the line to be immediately disconnected from the rest of the grid. To avoid this situation, lines are rated for a maximum electric current or power based on how quickly they can dissipate heat, just like the wiring in your home. When a line is operating at maximum power, it is said to be congested. A congested line limits the amount of electricity that can be traded between grid nodes, requiring electricity to be sourced from other generators that are potentially more expensive, and requiring power to be delivered to other loads that might not be willing to pay as much. Like transmission losses, transmission congestion contributes to price differences between grid nodes. Let's first look at an example of how transmission losses alone affect the market, and then we'll add in the effect of transmission congestion. As in the previous video, I encourage you to take a pause and explore these examples for yourself. Recall the previous video's example of two generators and two loads. Consider now that the generators G1 and G2 are located at a node A, and that the two loads L1 and L2 are located at a node B. The two nodes are connected by a transmission line with 75% efficiency. This is an unrealistically poor efficiency for illustrative purposes. The optimization problem becomes maximizing the welfare subject to the constraint that the total quantity bought, QL, must equal 75% of the total quantity sold, QG, meaning that for every 1 megawatt generated, only 0.75 megawatts are delivered to the load, the rest being lost to heat. This is a linear constraint, but would be quadratic if modeling the line's electrical resistance. Of the two quantities QG and QL, either can be chosen as the optimization problem's sole decision variable, from which the other quantity can be calculated via the efficiency. And here is our solution. The welfare has decreased from $47 per hour in example 2 to about $33 per hour in this example. The $13 per hour difference is the cost of having to transfer power between the generator and load nodes via lossy transmission lines. In this example, the producer surplus happened to stay the same at $12 per hour, while the consumer surplus is decreased with the introduction of transmission losses. So in this example, only the consumers incurred the cost of trade. However, in general, the cost of trade is paid by both producers and consumers. And this does not mean that trade is not worthwhile. On the contrary, in this example, transmission lines allow the generator and load to find each other, and trade in general provides more optimal buying and selling opportunities for market participants. Now assume that the transmission line between nodes A and B has an 8 megawatt limit, which is lower than the optimal power injection of QG star 9.3 megawatts that was previously determined for the line. With transmission congestion, the solution is now QG star of 8 megawatts, QL star is 6 megawatts, PA star is $4 per megawatt hour, and PB star is $8 per megawatt hour. And this is shown. The welfare is now $31 per hour, which is about $2.6 per hour lower than in the non-congested case. Indeed, congested lines generally reduce the system welfare and affect the nodal prices, this example being no exception. In this example, the loads pay QL star times PB star of $48 per hour, but the generators are paid only QG star times PA star of $32 per hour. And this difference is known as congestion rent and is collected by the system operator. Now consider that only generator G1 is located at node A, while generator G2 and both loads are located at node B. The optimization problem becomes maximizing welfare subject to the constraint that 0.75 times QG1 plus QG2 equals QL. Any two of these three quantities can be chosen as the decision variables. We'll use QG2 and QL arbitrarily. We can visualize this optimization problem as this 3D surface. The parallelogram shape of the surface, as viewed from above, is determined by the above constraint and by the fact that QG2 must be between 0 and 10 megawatt hours. And the solution to our final example is as pictured. Thank you for learning about electricity markets with me. You can learn more about this and other technical topics on my blog or by visiting me on LinkedIn. Thanks.